Why is the golden ratio an irrational number? Have you ever wondered why the golden ratio is such a special number? This fascinating concept is not just a simple fraction. It has a unique property that makes it stand out in the world of mathematics. The golden ratio, often represented by the Greek letter phi, is an irrational number. But what does that really mean? Let's break it down. To start, an irrational number cannot be expressed as a simple fraction of two integers. This means you cannot write it as a ratio like 1/2 or 3/4. The decimal representation of the golden ratio goes on forever without repeating. This quality is what makes it so intriguing. The golden ratio is defined mathematically through a specific equation. If we take two positive quantities, let's call them A and B, where A is greater than B, the golden ratio satisfies the equation, A plus B / A is equal to A / B. To simplify things, we can set B equal to 1. This leads us to the equation, phi plus 1 / phi is equal to phi. When we rearrange this, we arrive at a quadratic equation, phi squared minus phi minus 1 equals 0. By using the quadratic formula, we find that phi equals 1 plus the square root of 5 divided by 2. This value is approximately 1.61803. Now here's the key part. The square root of 5 is an irrational number. Since the golden ratio is derived from this square root, it inherits that property. Therefore, phi cannot be expressed as a fraction of two integers, confirming its status as an irrational number. Interestingly, the golden ratio is considered the most irrational number. This means it is the hardest number to approximate closely by fractions compared to other irrational numbers. This property has real-world applications, especially in engineering and nature. For example, when two frequencies are in the ratio of 1 to phi, they resist locking into resonance, which can be beneficial in various designs. When we look at number sequences, the golden ratio appears in the Fibonacci sequence. As you progress through the Fibonacci numbers, the ratio of consecutive terms approaches phi. This connection highlights how deeply intertwined the golden ratio is with natural patterns. In geometry, the golden ratio shows up in the proportions of the golden rectangle and in certain shapes like pentagons. Its unique properties contribute to the beauty and harmony we often see in nature and design. In essence, the golden ratio is irrational because it is defined through an equation involving the square root of 5, which is itself irrational. This fascinating number not only defines its mathematical character, but also influences patterns and phenomena across various fields.